Lorenz invariant. Since the concept of Lorenz invariance will play an important role, I've decided to actually call it Lorenz invariant classical field theory. So
are you able
I thought I'd start with some introduction and motivation. So the fundamental forces of nature that we know about are gravity, electromagnetism, and the weak and strong nuclear forces. And as you will see during the during your program here, during the lecture courses, these are described by what are called field theories. Okay. And what is a field theory? Well, as in all kind of models in physics, it's a mathematical model whose variables are quantities called fields. And the fields will play an important role. I mean, we're going to introduce fields in this course, and there will be fields essentially in all of your courses. Now, this mathematical model is usually called general relativity plus the standard model of particle physics, or sometimes GR plus SM. And one of the goals of your studies here will be to have understood what these things are, what general relativity and the standard model are. And I wanted to say something since this is the first week of the program. The general relativity and the standard model is really the most successful scientific model that has ever been conceived by humans. It's, this model has passed tens, maybe hundreds of thousands of rigorous experimental tests. Okay, and as I said, as the course goes on, you'll be learning more and more about, as the courses go on in the diploma program, you'll be learning more and more about general relativity and the standard model. Now, this particular course, Lorenz invariant classical field theory, is a step towards understanding GR plus the standard model. And really, it's an introduction to what fields are, how to work with fields, and Lorenz symmetry. The standard model of particle physics is an example of what's called a quantum field theory. So in this course, we're going to be talking about classical field theory. In the other courses, you'll be learning quantum field theory. And what quantum field theory is really the result of trying to merge special relativity, which is based on Lorenz invariance, with quantum mechanics. And as I said, quantum field theory is really the framework within which the standard model is constructed. And actually not just, you don't just apply quantum field theory to the standard model, but it has a, it can be applied to many physical systems, different condensed matter systems, for example. And really, at its beginning of its life, when you learn what the standard model is, the thing that you write down to begin with is a Lorenz invariant classical field theory, which is the kind of thing we're going to be focused on in this course here. Okay. And so this course is all about Lorenz invariant classical field theories. By the way, the terminology CFT usually refers to what are called conformal field theories in the literature. So I don't want to get you confused by that. So CFT is not conformal field theory. related subject. Just to, because the administration and so on are using CFT as the abbreviation for this course. It's not about conformal field theory. Okay, so the general outline of the course will be, we'll begin today with a description of what special relativity and Lorentz symmetry is and are. Then we will go on to introduce fields and sort of explain that the point partly that in order to have Lorentz invariant quantum mechanics, really you have to go to field theory in some sense. And with these fields, we will be trying to understand mathematically how classical fields get the physics of classical fields, and that involves things called Lagrangians, Hamiltonians. There'll be other types of symmetries that we will see, and then we will talk in the last part of the course about interactions of these fields. Now, I'm not recommending any particular text, but Landau and Lifshitz Volume 2, which is called The Classical Theory of Fields, contains a lot of relevant material. So I recommend you having a look at that, especially for the relativity presentation that I'm going to follow today. Sort of follows the logic of Landau and Lifshitz presentation, which is chapter 1 of this book. The slides, which are the lecture notes as we go along, I'm going to do most of the lecture notes on this my iPad here. And these will be made available regularly for you to have as a reference. And of course, then there is the video recordings. And as you know, as you probably know, the lectures are on Tuesdays, Wednesdays, and Thursdays. Some of these days, as we get going, will be for exercise classes. So we have a tutor for the course, Ida. She's one of the postdocs in our high energy group. And once we've got going, there's going to be weekly problem sets, which ideally should be completed weekly as well. Okay, so are there any questions before we begin about the structure or anything that I've said so far? Jessica, you've got your hand up. Sorry, I just noticed that. Did you want to ask something? Oh, you put your hand down. Okay. Does anyone else have any? Does anyone have a question? Indira.
Yes, please. I wanted to ask about the recordings and about the weekly problem sets. Where can we download them?
I don't know how quickly the recordings get posted, but there's a ICTP Diploma YouTube channel.
Oh, okay.
And I think they're also on there's ICTP TV or on the Diploma pages, but you,
Okay.
so actually I don't have a very precise answer to your question, but you can just email the Diploma office and ask if you can't
Thank
find
you.
them online. Okay. And the problem sets will be, well, you'll see some exercises in the, in here as we go along, and then I guess we'll collate them and distribute them to you by email. Jessica, you've got your hand up again.
No, Professor.
Oh, no, it's not your hand, it's my mouse. Sorry. Apologies. The mouse is
Okay.
the hand, and it was resting there. Okay. I think someone else wanted to say something or ask something. No? Okay. So let's start then with special relativity. And what we're going to do today is essentially derive the theory, Einstein's theory of special relativity and its mathematical consequences. I mean, essentially following Einstein's logic, but there's a beautiful presentation of it in Landau and Lifshitz. So first of all, in order to just talk about physical processes, we need a system of reference, meaning that we need to say where some physical event happened and when it happened. So we need coordinates and clocks, or equivalently ways to specify positions and times. Now, there exists systems of reference that we're going to, or coordinate systems that are most important in special relativity, are those pertaining to freely moving objects, which are not acted upon by any external force. So such an object will be in uniform motion. Let's say it'll be moving with respect to another object with constant velocity. So these frames are called inertial frames. And if any two such frames move uniformly with respect to each other, then if one of them is inertial, the other one must be inertial, because the relative velocity between them is constant. Okay. And if that is so, one can construct arbitrarily many inertial frames. And the frames themselves are related by what are called Lorenz transformations. And then by the end of today, or sometime tomorrow, in tomorrow's lecture, we will have understood basically what a Lorenz transformation is. Okay, so special relativity, or Einstein's special theory of relativity, is based on the relativity principle and one other assumption. The relativity principle is the statement that the laws of nature are identical in all frames of reference, all inertial frames of reference. What that means is that since we actually describe the physical world through mathematical formulae and equations, it means that the form of any formula which describes some physics in one inertial frame will take the same mathematical form in any other inertial frame. So as we will see, since we can transform the space and time coordinates from one inertial frame to another inertial frame by a linear transformation, a Lorenz transformation, the equations describing the physics in one inertial frame get transformed to some equations in the other inertial frame, but you'll be able to see that those equations are actually identical. If they're equations for physical laws, like, for example, as we will see, Maxwell's equations. Okay. Now, in sort of non-relativistic or classical mechanics, as Landau and Lifshitz call it, the interaction between particles or objects is described by a potential, which is some function of the space coordinates, x1, x2, x3, or x, y, z. Now, in this description, interactions between objects are actually instantaneous. So they actually take place at one given instant in time. For example, if you have a system of particles with some potential, if you change the position of one of the particles, the other particles in the system respond immediately, according to classical mechanics. But clearly, experimentally, we've seen that interactions cannot happen instantaneously. Okay? They take time to propagate. So that leads to this concept of signal velocity, or the velocity of propagation. And from the principle of relativity, since the laws of physics have to be the same in all reference frames, it means actually that the velocity of propagation of signals must be the same in all inertial frames. And this propagation velocity is the velocity of light, whose speed, usually called c, is some very large number, as you know anyway. And in vacuum, this is approximately 3 × 10⁸ meters per second. So the sort of, c turns out, c is a very large number. As an absolute velocity. So most phenomena in nature do not involve velocities of physical objects close to the speed of light. Speeds close to the speed of light. So for most intents and purposes, this very large value can be approximated by infinity, and in that limit, the kind of effects that we will be talking about in relativity will not be observable, and in the c goes to infinity limit, relativistic mechanics becomes classical mechanics. But the reason that we are, well, there are many reasons why relativity is important. And one of them is that we want to understand the structure of matter at very small scales, and the only way to probe very, very small scales directly is through extremely high energy experiments, such as those that are going on at the Large Hadron Collider. And in order to probe nuclear and subnuclear distances, one requires particles of extremely high energies and extremely high velocities. So the protons in the Large Hadron Collider, when it's at operational energy, are moving very, very close to the speed of light, because their energies are much, much larger than thousands of times larger than their actual, the rest mass of the proton. Okay, and it turns out that to a very high degree of accuracy that the principle of relativity is correct, namely that the words we'll use, and you'll learn what these words mean as the course goes on. The world is Lorenz invariant to a very high level of accuracy, so at very, very small distances. Okay, so this principle was formulated by Einstein at the beginning of the 20th century, and supersedes what's known as Galilean relativity, which is sort of the which is based essentially on this infinite propagation speed. And in the Galilean model of mechanics, or what Landau and Lifshitz call classical mechanics, time is absolute. So there exists just one time coordinate for all spatial reference frames. So in Galilean relativity, you can have relative motion, but so you can consider frames which differ in their spatial coordinates, but the time coordinate is the same for all of these frames. And this simply cannot be true in relativity, in special relativity, because in the Galilean world, signals will arrive, faster or slower depending on the observer's direction. If I'm traveling towards a signal, it will arrive faster than if I'm traveling away from it. But experiments have shown, and this goes back to Michelson in the 19th century, but of course many experiments have subsequently been done to show that the speed of light is constant in all inertial reference frames. So in other words, it does not depend on direction of motion, for example, of the Earth compared to where the signal is coming from. And as you probably will have seen, C has been measured to pretty high level of precision. Okay, so let's elaborate this a little bit. So let's consider two inertial frames. I'll call them capital K and capital K prime. So K prime relative to K has the same Z coordinates and the same Y coordinates, but is moving relative to K along the X direction. Okay, so its X coordinate is, I'm calling it X prime because it's not the same as X. And later on, we'll see how to get from X to X prime. And now in K prime, we've got a point A and a point B and a point C. Let's say that A is a light source. And at some point in time, which we've not drawn the time coordinate yet, a signal is emitted from A which propagates to B and C, and B and C in the K prime frame are the same distance from A. Okay, so they're equidistant along the x-axis. So, you know, the light source is moving along with K prime in the K prime frame. So in K prime, the signal arrives at B and C simultaneously because the distance is the same. So this is not true in the frame K, since B moves towards a signal and C moves away from it. So the point there is that the times will be measured differently. The time that the signal arrives at B and C will be different in the K frame, which means that time cannot be absolute. Rather, it's also a relative concept, as we will elaborate more today, that moving clocks moving relative to one another measure different times. That's one way of putting it, and we'll see how that works in detail today. So to get more as we go on, we're going to get more and more mathematical. So in order to do that, we want to introduce the concept of intervals. So let's consider these two frames again, and let T1 and T2 be the times in K when a pair of signals are measured. And similarly, we'll call X1, Y1, and Z1 the position at which the first signal is measured, and X2, Y2, Z2 the position in K when the second signal is measured. Now, there are two measures of the distance between these two events. One is you just take the difference in time, which is T2 times T1, and then you multiply by the speed of light. That gives you the distance. On the other hand, you can take the Euclidean distance in space between them. So you just take x2 minus x1, take its square, and do the same for y2 and y1 and z2 and z1. And that gives you a distance. So these things have to be the same, because C, according to relativity, it's the same in all inertial frames. So now what we get is this equation that we have these two equations now. One is in the frame K, and the second is in the frame K prime. So it means that the interval between two events is 0 in all inertial frames. Okay, now for infinitesimally close events, we consider an infinitesimal version of the interval, okay? So we write that as ds squared is equal to c squared dt squared minus dx squared minus dy squared minus dz squared. So that just follows from thinking about these formulae infinitesimally. So instead of x2 minus x1, we now have delta x1. And you see the signs of the spatial terms are opposite to the sign of the time term. That's really crucial. And it just comes from That's really a fundamental fact about relativity, and it comes from the fact that these two things are equal. And that sign is crucial. When you take the square and set the interval to 0, you get this sign, and that sign, the relative sign, is really crucial mathematically, and then has many physical consequences. It sounds simple, and it is simple, but it really has a lot of consequences. And so here, we've just taken an infinitesimal version of that. So in the brackets here, there's a couple of notes. The second one is that I could have used a different sign convention. I could have had 1 minus sign and 3 plus signs. All that's important is that there's an overall relative difference between the space and the time. So just be warned, different textbooks use different conventions. I'm going to stick with the convention in Landau and Lifshitz, which is the one with mostly minus signs. I could have chosen the other, mostly plus sign convention. This has no physical, I just want to emphasize that the difference between these two choices of sign has no physical consequences whatsoever. The first note in the bracket here is that this defines a space-time geometry, which is called Minkowski space-time. So we usually think of the space-time, which is the set of values of the coordinates x, y, and z, and t, as defining a 4-dimensional space-time manifold. And you'll learn more about what these things are, for example, in the general relativity course. And just to make connection with that course, this metric, this thing that I've written down here, this infinitesimal form of the interval, defines what's called the Minkowski space-time metric geometry. But we don't need to worry about those words in this course, apart from, maybe the word Minkowski. Now, if the infinitesimal interval is 0 in one inertial frame, it has to be 0 in any other inertial frame. And that actually means that ds has to be proportional to ds prime. So the first exercise I want you to start looking at is the proof that the proportionality constant between them is actually 1, which means that the interval between any two events is the same in all inertial frames. And mathematically, this is how the constancy of the speed of light gets manifested in formulae. Okay, I think also one thing I should have said at the beginning, it's tiring to sit for 90 minutes in front of a screen, so we'll usually have a 10-15 minute break every lecture. This is a bit, maybe slightly later than I would have taken it before, but we had the introduction and so on that took a little bit of time. So according to my clock here, pause the recording. According to my clock here, it's 10 to 3. So I'm going to say let's take 10 minutes and we'll come back at 1500 Trieste time, or 10 minutes from now. welcome back. Start the recording again.
Sorry, I have a question.
Sure.
Would you go to the page where you you write if ds is equal to 0, then ds prime is also equal to 0 in other inertial frame. I didn't understand how this implies that ds is proportional to ds prime, because any transformation that preserves the 0 of ds works also, I think.
Any other?
For example, if ds prime would be equal to ds prime equal to ds times t dou x, for example, not a constant of proportionality.
Oh, the transformations between frames are it's, as you'll see, that the transformations between frames are linear transformations by constant matrices.
Mm-hmm.
So that's, you can't have situations like the one you described.
Mm-hmm.
Transformations don't depend on the coordinates.
Oh, thank you. So by saying that the transformation is constant and the 0 of this interval in a space-time preserved, then we can conclude that ds is proportional to ds prime.
Yes. Yeah.
Okay. Thank you.
Yeah. Okay. Now we're going to look at spend a few minutes looking at different types of intervals. So we're going to give a classification of the types of intervals that can occur. Okay. So the question we'll ask is that, does there exist a coordinate system in which two events occur at the same point in space? So they're at the same point in space, but different points in time. Okay. So we introduce some notation. T12 is the difference between the two times which separate the events, and L12 squared is the difference of the sum of squares of the differences between the positions. So in one frame K, for example, we can write S12 squared is C squared T12 squared minus L12 squared. And then let K prime be the frame in which the coordinates are labeled by primes. And let that be the frame in which the two events occur at the same point in space. So the relativity principle tells us that these intervals are the same. So in the K prime frame, if they take place at the same point in space, means L12 prime is 0. So the interval there is just C squared T12 prime all squared, which clearly is greater than 0, which means that the interval, which would be the square root, is real. And these events are, these separations are called time-like separations. Okay, just a name that we use. Similarly, if you do the opposite, you can ask about a coordinate system K prime in which two events occur at the same time. So they occur at the same time, but at different points in space. So then T12 prime is 0, and the interval squared is minus L12 squared, which is clearly less than 0. So the interval for such events is imaginary. And these events are called, these intervals are called space-like intervals. Okay? And space-like and time-like intervals are the only two types of intervals that you can have, so that they're actually invariant concepts, as we will see. So if we suppress the y and z directions, and we can just think about a two-dimensional space-time with a coordinate x and a time coordinate t, so we're just in one dimension of space, then we can think about an event which occurs at the origin, O, right at the center of this diagram. And once the event has occurred, the diagram gets separated into these different regions. So there are two, what I call absolutely separated regions. And there's an absolute future of the event O, and there's an absolute past of the event O. So the point is that the absolutely separated region means that any other event which occurs in that region will always have a different x coordinate to O, a different x position to O. And similarly, in the absolute future, any other event will occur after O, meaning that there's no frame of reference you could find in that region that would have the same time coordinate as O. The reason for it is that, maybe I wrote this on here, see these diagonal lines, you know, P to S and R to Q, those are the lines along which light would travel. So any object moving at the speed of light would live along those two lines, because that's the solution of x squared. Those two lines are the solutions of x squared equals c squared t squared. And the region inside those lines, which is the absolute future and the absolute past, are referred to as light cones. So you have the future light cone of O and the past light cone of O. So starting from O, any object moving with less than the speed of light, which by definition has to be the case, allows you to conclude that any other event will occur, any other event in the future of O, whatever O does from that point on, will have to occur inside the future light cone. Because in order to get outside of the future light cone of O, you would have to travel faster than the speed of light. Not possible. So you see that this this classification of intervals into space-like and time-like leads to this structure of any, and we sometimes call these things space-time diagrams. And if you can just consider the trajectory of any object in space and time throughout its history, it traces out a path in x and t, which we can call the world line of the particle. And at every point on that world line, you can draw the future light cone and the past light cone. So signals can only reach O if they originate in the absolute past of O. That's another way of saying it. Now, in 3+1 dimensions, this light cone would be defined by the equation x squared plus y squared plus z squared minus c squared t squared is equal to 0. Okay, and I've tried to draw it here. That would then, if you add in the other directions, you get this curve. It's actually a cone. Okay, so for the remainder of the lecture, we're going to discuss the times measured by clocks, which are in relative motion to one another. All right, so if you have a moving clock, you can naturally associate a frame of reference to it, which is the time that is being registered by that clock and the x, y, and z coordinates of that clock. And so if you've got different clocks, one can consider, if you've got different clocks in relative uniform motion, then you get natural inertial reference frames for each clock, each such clock. So if we're considering clocks moving relative to us, in our time interval, we have dt, the clocks will travel some distance, which would be the square root of dx squared plus dy squared plus dz squared. In the clock frame, because the x and y and z coordinates are not changing, so if the clock frame is defined with the primed coordinates, its distance would just be c squared dt prime squared, its infinitesimal distance squared. Okay. So if you rearrange that formula, you get that dt prime is dt times the square root of 1 minus the distance, infinitesimal distance squared divided by c squared dt squared. So just to go back, so you can see I'm just rearranging this formula and taking the square root. But the point is that, you see, dx by dt would be the velocity in the x direction, dy by dt would be the velocity in the y direction, and dz by dt the velocity in the z direction. So the sum of squares of the infinitesimal divided by dt squared is actually the square of the velocity vector. So I can substitute this into here, and I get this equation here, that dt prime is actually dt times the square root of 1 minus b squared over c squared. Or I can also integrate that between the two times, t2 prime minus t1 prime. Now, so this is how you define the proper. These two equations here, if you like, give you the definition of what is called proper time of some moving object. Now, comparing the left and right-hand sides of these formulae and using the fact that the square root factor, 1 minus v squared over c squared, is always less than or equal to 1, tells us that the proper time of a moving object is less than the proper time of an object which is at rest relative to that moving frame. Another way of saying it is that moving clocks go more slowly than clocks at rest. And this is something which is very well experimentally verified. Okay, so now we're building up now towards defining and mathematically Lorenz transformations. So given two frames with coordinates tx, y, z, or t prime, x prime, y prime, z prime, how do we express the primed coordinates in terms of the original ones? And the answer to that is Lorenz transformations, which are the mathematical foundation of relativity theory. I'm going to introduce some words here, which will come back later. So one thing we say is that Lorenz transformations are the symmetry group of special relativity. So they form a mathematical object called a group, and groups play an important role in theoretical physics, especially in particle physics and general relativity. So we can define a Lorenz transformation as a linear transformation which leaves the intervals invariant. In particular, if you make a linear transformation between the primed and unprimed variables, that means just some 4x4 constant matrix. So the matrix will depend on some parameters, but those parameters are not t, x, y, and z, so constant in that sense. It has to be invertible because you want to be able to go from one frame to the other. So if I just multiply this equation by its inverse, by the inverse of m, sorry, I'll get the inverse transformation. And this matrix is defined in such a way that it leaves the quantity c squared, the quantity at the top of the blackboard, invariant. Okay, now Lorenz transformations come in two kinds, can be classified into two kinds. Rotations, what are called rotations, and what are called boosts. The rotations are the transformations which don't change the time coordinates in the two frames, i.e. they mix only the space coordinates. So for those transformations, the matrix will look like the one I've written here. There's a 1 in the top left because it will take t prime to t. And then you can have a non-trivial 3x3 block which acts only on the spatial coordinates. Now, since we want to preserve the intervals, we have the above equality. And that means that x squared plus y squared plus z squared must be the same in the other frame. So this subset of Lorenz transformations are the set of 3 by 3 matrices, invertible, that preserve x squared plus y squared plus z squared. So now we're going to start introducing some notation. Let's relabel, let's introduce an index I, which runs from 1 to 3. And x1 will be x, x2 will be y, x3 will be z. So the sum of squares, we write in the following way. That, so you see the thing on the left-hand side, which is x1 squared plus x2 squared plus x3 squared, I've written as the sum over I of xi times xi. The thing on the right-hand side has x with an upper I and x with a lower I. And because you have a repeated label, one upper and one lower, you sum over that label. So this is Einstein's summation convention, which allows you to simplify formulae. Okay, so it's just a definition. And the reason that we have to have one upper I and one lower I is that you can think of this as the dot product between a row vector, x upper I, and a column vector, x lower I. Okay? So if you take the dot product of two vectors, of those two vectors, you get the quantity which is the sum of squares. So that's the important notation that we need to get used to. So in this notation, we can write R, the entries of the matrix R in this way, as R upper I, lower j. And you see that when I'm writing x prime j as the transformation of x lower I, the I index is summed over, and that's just matrix multiplication of a matrix times a vector. So for those of you who are not familiar with this type of way of writing matrix multiplication, I urge you to rewrite the right-hand side as what it is. It's R1j x1 plus 2j x2 plus, sorry, I'm running out of space, but R3j x3. And then if you fix a value of j, say j equals 1, which shows you what what the transformation of what the new x1 is. Similarly, the transformation of the row vector, see the row vector is just the transpose of the column vector. So the a row vector is naturally acted on by matrices from the right-hand side, because it's just this here is just R dot X, transposed, and transposing reverses the order. So the quantity of interest, which is the sum of squares, transforms into this quantity here. And now I've been quite careful to introduce appropriate new labels. This, for example, I've introduced the K label. The point of that is that if I'd have written here instead I and I, that would be confusing because I've already got an upper I and a lower I in the first factor of the formula. And so you wouldn't know which I to sum over if you did it that way. And if you summed over the wrong one, you would get the wrong answer. So therefore, I've introduced a new label. So summed over labels, you can call them anything you like. I could have, I could have chosen any symbol there. But it's important that it's not the same as any other previous symbol that's being summed over. And so we require that this quantity here is equal to the thing we started with, which is the sum of squares. And that means that this product of matrices in the middle, so you see here, the J label is summed over, and that's just matrix multiplication. So this is the product of the transpose of R with R. And the condition that we're looking for, that the sum of squares is invariant, is the condition that the transpose of R with R is the identity matrix. So this is just a notation for the identity matrix. So the entries here equal 1 if I equals K and 0 otherwise. And a matrixy, sort of more compact way of writing it is just R transpose dot R is equal to the identity matrix. So these are the conditions that we have to solve for, and such matrices are called orthogonal matrices. So we get the statement that the rotations in M, or in other words, the subset of Lorenz transformations which are rotations, are orthogonal 3×3 matrices. So these actually, even though I haven't defined group, but we will next time, tomorrow, we'll pick this up. This forms an actual group called O3, the orthogonal group in 3 dimensions. Physically, what these things are simply just rotations in space, the usual spatial rotations that you will have seen in quantum mechanics courses and other courses previously. So we're going to stop there, but in terms of the lecture, but are there any questions? Okay, so tomorrow we'll go on to discuss the rotations, but then the rotations, since they preserve the time coordinate, are just, this is also a symmetry group of Galilean relativity. The more interesting from the point of view of relativistic effects elements are the boosts. So tomorrow we'll also go on to discussing the boosts, which are the transformations which take one frame and boost it relative to another. And that's how you create the transformations between relatively moving inertial frames. All right, so yeah, I've stopped the recording.